Welcome to the Explainer. Today, we're zooming way in to look at the microscopic choreography of the die attach process. It's this incredibly high-stakes, hyper-precise manufacturing step that literally keeps our everyday electronics from melting down or just, snapping in half. If you've ever wondered how the brain of your computer, your smartphone, or even your car actually survives the brutal real world out there, well, this is exactly where that magic happens.
Think about it for a second. How do you permanently glue a microscopic brain to its body? Because the die attach process isn't just some dry manufacturing step on an endless assembly line, it's a critical mission. We're taking an incredibly fragile semiconductor die and giving it a permanent, rock-solid home where it has to survive extreme heat, intense physical stress, and constant electrical demands for years on end.
Okay, let's dive into this. Here is our roadmap for today. First up, 1. The die attach mission. Then, 2. Selecting and dispensing materials. Next, 3. The precision placement, followed by 4. Curing and cleaning, and finally, 5. Final quality control.
Section 1. The die attach mission. So before we get into the how, we really need to establish the why. When we build these devices, we're constantly fighting 3 true enemies: heat, mechanical stress, and electrical resistance. When engineers talk about gluing a chip down onto a substrate or a lead frame, they're actually talking about an intense feat of engineering, completely designed to conquer those 3 specific enemies. We absolutely must provide robust mechanical support, otherwise the die shatters if the device gets dropped. We have to ensure efficient thermal dissipation because these chips generate serious, potentially damaging heat. And lastly, depending on the design, we have to establish a flawless electrical interconnection, which we often do using conductive adhesives or eutactic bonding.
And here's how this builds into our standard process flow. This highly structured 6-step loop is going to visually anchor our entire journey today. It all kicks off with step 1, material prep. We're prepping the semiconductor wafers by back-grinding them to the perfect thickness, mounting them on dicing tape, and carefully sawing them into individual die. At the exact same time, we're meticulously inspecting the incoming substrates to catch any oxidation or coplanarity issues. Once everything is prepped and cleared, that's when we move into the actual attachment.
Section 2. Selecting and dispensing materials.
All right, let's shift our focus to the chemistry side of things for a minute. This is where we choose the perfect bonding armor and prep the ground for our chip. And this brilliantly illustrates how the power level of the device entirely dictates our material selection. For low to medium power applications, we're generally using epoxies and adhesives. These can be films or pastes, and they can even be packed with silver flakes to make them electrically conductive. But if you're dealing with high-powered devices that need superior thermal and electrical conductivity, you've got to step up to solder alloys, like gold tin, tin silver, or lead tin soft solders. Finally, for those extreme wide-band gap devices like silicon carbide and gallium nitride, we use sintered silver. It requires a high-temperature pressure-assisted process, but man, it creates an almost indestructible bond.
Once we've got our perfect material, we have to apply it accurately. We typically see 2 main liquid dispensing methods here. On one side, we have time pressure or auger dispensing. This uses incredibly precise dots or specific patterns like a spiral or a cross, specifically designed to prevent air voids and minimize any adhesive squeeze out. It's incredibly precise. Versus stenciling or screen printing, which deposits uniform paste layers across multiple package sites all at once. That method is built for raw speed and high-volume manufacturing. Oh, and quick side note, sometimes we actually skip the liquid entirely. Die-attach film, or DAF, is a really great alternative where a film adhesive is laminated right at the wafer level before we even start dicing.
Section 3. The precision placement. Okay, the materials are ready. We are now entering the absolute climax of the operation. This is the high-speed, hyper-precise drop where automated robotics completely take over. The microscopic choreography here is just incredible. First up is the ejection process. Tiny needle pins physically push the individual die up from beneath the dicing tape, while a vacuum collet swoops in and perfectly secures it from the top surface. Then, guided by ultra-fast optical recognition vision systems, an automated bonder perfectly aligns the die mid-air and drops it exactly onto the dispensed adhesive.
So the crucial point is getting the bond line thickness, or BLT, exactly right during this drop. This is the precisely controlled thickness of the adhesive layer sitting directly between the semiconductor die and the substrate. Think of it like the Goldilocks principle of manufacturing. If that layer is too thick, thermal resistance spikes and the chip will overheat and fail. If it's too thin, it can't absorb mechanical stress and the die will literally crack under the pressure. It has to be just right.
And what exactly is just right? Typically, we're targeting between 20 and 50 micrometers. To put that into perspective for you, that target is literally thinner than a single human hair. To hit a target that incredibly thin without cracking the ultra-fragile die, the robotics have to apply a hyper-calculated placement force. That precise force guarantees proper wetting of the adhesive and ensures a beautifully uniform thickness, locking the whole shebang perfectly into position before we turn up the heat.
Section 4. Curing and cleaning.
So the high-speed robotics have done their job. Now we kind of take a breath and move into the more deliberate, time-consuming baking and reflow processes. This is what locks that die in place permanently. Depending on the material we carefully chose back in step 2, the curing process is going to look vastly different. For polymer-based epoxies, the assemblies pass through thermal cure ovens, following very specific profiles, slowly ramping up to between 150 and 175 degrees Celsius for 1 to 2 hours to fully polymerize the resin. Versus metallic bonding, right, solder reflow or silver sintering, requires passing parts through a specialized reducing atmosphere reflow oven, or applying intense thermal compression pressure to form a solid, completely void-free metallurgical bond.
Now, sometimes all this extreme heating and bonding leaves a bit of a chemical mess behind, and that brings us to post-attach cleaning. This is an optional inline module. Basically, if our soldering or dispensing left behind any unwanted flux or organic residues, we absolutely wash it away right here. We use specialized solvents or deionized water washes to ensure the package is completely pristine before we move forward.
Section 5. Final quality control.
The die is perfectly placed, it's baked, it's meticulously cleaned. But the mission isn't over yet. It is time for the trial to see if our newly attached die can actually survive brutal scrutiny. We kick things off with non-destructive testing. First up is AOI, or Automated Optical Inspection. AOI is our primary external check, hunting for any die rotation, XY offset placement issues, or excessive adhesive squeeze-out that might cause a short. But we can't just look at the surface. That's why we bring in SAM, Scanning Acoustic Microscopy. Think of SAM like a microscopic medical ultrasound, peering deep into the hidden layers of the bond, hunting for dangerous internal delamination, tiny cracks, or hidden air voids right at the die-attach interface.
Now, what's really interesting about this slide is how strictly we have to monitor those hidden air voids we just found with the SAM ultrasound. For a part to truly be considered high reliability, those air voids typically must be kept strictly below 10 to 15% of the total die area. That means, at a bare minimum, 85% of that incredibly thin 20 micrometer bond line must be solid, flawless, uninterrupted contact. Because if there are too many air bubbles, heat simply gets trapped and the chip will literally cook itself to death. No way around it.
Finally, we have to prove the bond's raw physical strength. And for that, well, we have to sacrifice a few parts. This brings us to die shear testing. It's a purely destructive test. A machine applies a crushing lateral force directly against the side of the die, pushing harder and harder and harder until the mechanical bond completely fails and snaps. We do this to meticulously measure the mechanical bond strength, ensuring it complies with strict military-grade standards, like MIL STD 883 Method 2019. It conclusively proves that the bond is mechanically tough enough to survive the absolute worst the real world can throw at it.
The die attach process is just an incredibly complex, microscopic dance of chemistry, robotics, and thermodynamics that happens in a fraction of a second. So I want to leave you with this thought. With billions of chips produced around the world daily, how many flawless microscopic bonds were perfectly formed just while you watched this explainer? The sheer scale and precision of the microscopic assembly line hiding inside your own devices is truly staggering. Thanks for joining me on this deep dive, and keep wondering about the incredible hidden world inside your tech.